I am Frédéric Parain. I work at Oracle in the HotSpot runtime team, and my co-speaker is Bjorn Vardal from the J9 team at IBM. So today we'll speak about minimal value types from the VM perspective. In case you missed the slide of the previous presentation, you have one more time to read it. So value types for us is a very key element for the Valhalla project. And for the German perspective, the goal is performance, and only performance. How to achieve that? We want to flatten some data structure, so we have better spatial locality for better cache efficiency. We want also to exploit immutability and no identity properties to enable more JIT optimization that we cannot always do with object today. If you are following the Valhalla project, there is a number of documents named State of the Value that have been published. They are describing the project and the goals, but this is a mix of high-level semantics, like no identity, immutability, and also some very low-level optimization detail, how value types could be broken down in components on the stack. As the project moved forward, we realized that not all these ideas could be pushed into the JVM specification. In fact, many of them were implementation details. So we are preparing a spec for the minimum value type. You might be surprised that some aspect of value types described in the state of the values document do not show up in the specification. It's just that we are considering their implementation details, we're implementing them, but not specifying them. If we were designing value type for a new language, from a clean slate, it would have been much, much easier. The fact is we are adding value types to an existing, already very complex system. The Java platform is not only the Java programming language, as many of you know, we are supporting multiple languages, but we also have a number of features like GCs, GNI, GVMTI, reflection, serviceabilities, class loading, unloading. I'm missing a lot of them. All these aspects are impacted by the introduction of value types. And those features are also influencing the way we are designing value types so we can support them. Adding new features to a highly optimized code is already a tricky task. So we are being very careful about not breaking existing code, existing optimization just to put the value types in. So the goal of this presentation is to explain why some aspects of the JVM specification extension differ from the initial design document. We will show you how the promised optimization are implemented, even if they are not visible from the specs perspective. And we will also highlight some implementation constraints we are facing that make the value type story not as simple and straightforward were initially thought.
So MVT provides the goal is to provide some of the essential features of value types. And as Maurizio covered on Monday, we're doing this without language support. We're doing it with bytecode spinning in, that you can do bytecode generation and method handles. So no language support. But we're hoping that MVT is a step in the right direction. But the minimally part means we have to do some tiny little side steps to make it happen. So how do we do value types without actually doing value types? We do value capable classes. And Maurizio covered this a little bit on Monday, the value capable classes that you can define that is currently valid Java source. And then he said that we do some internal VM magic. So let's do some magic. So you get these annotated Java classes, they get loaded in as reference types, and we, if a user actually ends up asking for a value class, we derive that value class, and it's completely up to the JVM when that happens because there's no initialization really involved with it, so we can do it as lazily as we like. In J9, our derivation works like this. Well, let's quickly cover first. These are the J9 class data structures. So when we get a class file, we convert that into what we call a ROM class, which is really just different data structure representation of the same thing, all symbolic data. And then we put a RAM class on top of that, which is the live data, and then we also need to tie in the Javelin class object. So we can, initially when we started working on this problem, we just said, okay, let's create a second set of these data structures. The main reason for that was because they were, was that the proposal for MVT said that these were actually quite different. Like the DVC had all the fields, the VCC had all the methods, and there was some relationship between them. But as the spec evolved, we realized that these are actually a lot more similar than we thought. So we tried the other ditch. Do we really need anything other than just two Javelin class objects that, so we have some runtime distinction between the types? Got a little bit complicated, especially in the J9, because we couldn't, we had some, wanted to reuse some code. We needed to distinguish, are we working on a reference type or a value type? So we ended up with this representation where we basically have class mirrors. So essentially on the class file, converted to a ROM class, and we split it into two views. So that at runtime, when we, for example, try to do a get field, we know whether that get field is happening on a Q type or an L type. So to simplify going between these two types, we just tie them together. So now we have pointers from the DVC to the VCC. So some implications of that, the name is in the ROM class. So DVC and VCC ended up having the same name. That is not according to spec. But because we don't really expose that name, the only time you see it is in the constant pool, we're able to work with that. Another question is, what's the superclass of a DVC? Well, the ROM class says it's Javelin object. We don't think that's true. Currently, we just say you don't have a super type. Maybe it is object, maybe it is some kind of value super type, but it's a bit of an open question now, but it works currently in J9. Also, for example, we can't set the ACC value flag the way we're supposed to because, well, it's supposed to be set on the ROM class. Well, we're able to work around it. So in the constant pool, how do we discussed different ways of representing a value in the constant pool. We agree that we have to make some changes to make it happen. But the question is, should we, for example, then, so this is the current way the class is represented, right? You have a class that references a name. But do we then introduce value, or do we introduce some kind of generic type constant that can be a value, that can be a reference, that can be primitive? But deciding on correct constant pool representation is not really essential to getting this working. So we said, what did we say to complex CP changes? Not today. And we all happily and without any reservations agreed that the best possible way this could ever be done is name mangling. So we have this notation where a constant class, if it is a Q type, has this semicolon Q notation in front of it. And officially the name of the DVC is the foo dollar value part, and then the rest of it is an escape sequence. And as you can see, we don't need that semicolon when we talk about them in the descriptor. The problem with the constant class is that it doesn't include that type character, like L for reference type, so a Q. But we needed that Q, so we had the semicolon in front because that's not valid in a class name. But in a descriptor, for example, it becomes just Q foo dollar value. So in J9, again, as I mentioned, we don't actually have different names, but because both the prefix and suffix are both predictable, it's semicolon Q and dollar value, we just drop both, and then we can load the value capable class, which knows where the dry value class is, so we have what we need. Fred, do you want to cover hotspots?
So in hotspot, we are doing the same mechanic to derive a value class from the value capable class, but we are doing slightly differently. On first touch of the derived value class, the JVM just initiates the process of derivation from the value capable class. We have a Java helper to do that, so JVM callbacks the Java helper, passing the class loader and the value capable class in argument. From the value capable class, the Java helper generates a byte array containing the definition of the derived value class, and then call define class to inject it into the system dictionary of the JVM. Then the Java helper returns. Then the JVM performs a lookup on the system dictionary, and great, we find the derived value type, derived value class, and then perform the association between the value capable class and the derived value class. So in HotSpot, we have two completely independent metadata, and they are just loosely coupled with a reference from the derived value class to the value capable class. All this derivation process is just a workaround we have because of the minimal aspect of minimal value type, and we don't have the language support. For us, the real work starts when we have the value classes defined in JVMs, because this is where we can start optimizing. The first optimization has been flattening, and the goal is to have a better spatial locality, especially for arrays, and also to reduce the footprint by removing pointers and headers. Today, if you have an array of objects, you have in fact an array of pointers, and each pointer refers an object with a full header. We need the header because each object, each element of the array has its own identity, and we need the header to keep track of this identity. If we have here a value type, this value class point, value types do not have any identity, so we do not need the header to keep track of the identity of each element. And the array is homogeneous. The type is the same for every element, so we can factorize and have the type information only once. So we can flatten arrays, have only the fields of each element stored in a contiguous chunk of memory, and having the type information retrieved through the metadata of the array itself. It works very well with the class point, which has two fields that are int, but flattening is not that easy if we are looking at other value types. Here we have value type VT1 with a long and a byte. In the JVM, we have to deal with alignment constraints for each type to preserve performances. So the layout of the array, this is one that we have today. We have to add padding from time to time just because some types have alignment constraints we have to respect. We have explored some other more complex layout to get rid of this padding, but none of them have been implemented so far. If you look at the second value class, VT2, which has an object reference string in it. This makes the life of the GC harder. Before value types, the life for GC was very simple with arrays because primitive arrays have no reference in them, and object arrays are only references. Now, each array of value types we need a special map, some information that helps the GCs to find where the references are, because they are spread across the whole array. So value types, by definition, are immutable. But the containers, the arrays or field containing value types might not be immutable. And if they are not immutable, there is a risk of having concurrent reads and writes that could lead to tearing. This is still an area of exploration right now. What we are almost convinced with is we need some declaration site information about is there some atomicity requirement for an array of value types or field containing value types. Because the JVM might need to do some special work to ensure that atomic updates are possible. And then the JVM could decide implementing different strategies like flattening anyway if this value type is small and smaller than the size of the atomic operations, can decide to not perform any flattening for big value types. We might insert some seclock per field or per object so we have a way to ensure atomicity of the updates. We have some issues with VarHandles because VarHandles are trying to do atomic operation without any preparation work on the declaration side, so we have to work with that. We have currently nowhere in the language to express some constraint about the element inside an array, just the array itself. So this is still an open question. Do we need to extend the syntax of arrays or not? All this work are exploration work, and you don't have this in minimal value type yet. One important question for us is steering really an issue for you? We'd like to have your feedback about, do you think this is an issue for you, or do you just don't care? And please tell us.
So I won't go through these bytecodes again. They were covered on Monday. But what I'd like to point out here is that none of them actually talk about, they all talk about behavior. They don't at all talk about implementation with respect to data layout or backing storage or anything like that. So we could specify that behavior, of course, but as we just heard, the different implementations have different limitations. So instead of specifying the optimizations we want, we just let the specifications add capabilities like no identity, immutability, and then we're free to do the optimizations we like to do. And in terms of J9's implementation, that made the starting point very easy because always allocating on the heap is a completely valid approach to this. So we start off there and then we add real value support as we go along. So the first area where we wanted to add real value type support would be the flattened arrays. And the reason why we want to do that is because that is something that is shared with the JIT. So you could do a lot of optimizations of the Java stack, but it's not really going to pay off. As soon as you leave the interpreter, all the optimizations are gone, and you're only left with what you had in the heap. So flatten arrays, flatten fields. Let's see. So if we take a step back and look at state of the values, what it actually said, it suggested that values should have a flat representation on the Java stack and in registers. And it further suggested that values on the stack should be broken into their slot size components. So a 3D point of 3 ints would then get stored in 3 slots. So let's explore what that would look like. So we have a value class record. It has ints, height, width, and depth. And what record add will then push a record R onto, in record add, record R will be pushed onto the stack as an argument to DB associate, and then it also pushes a string. So the field-wise pushes will look like this. So you get the slot for each. So the fact that if you're not familiar with the Java stack here, basically the pending pushes, so we push height, width, depth, string, and because the pending pushes and the arguments both deal with fixed size slots, we just use those pending pushes as the arguments into the method we're invoking. So DB associate also knows about record. So it says, oh yeah, I'm expecting a record, and that should be those 3 ints. So that's all good. It expects the right thing. Unfortunately, it's really easy to break. Because what if we recompile record with a new field like weight? And obviously, I hope adding a field to a value class is a compatible change. So record add now will push 4 ints. Let's see. Yeah, so 4 ints, and then, so the extra weight, and then the string s at the end. But DB associate still only expects the 3 because it wasn't recompiled. So we could try to solve this. We could try to have some kind of runtime resolution of value types where you ask a value type for its descriptor string and slam that into your method descriptor. But it's starting to sound like the approach suggested by state of the values wasn't really the best solution. Definitely a costly one. So, Fred, do you want to talk about some alternatives?
Yes. So the work on the slot design kept us busy for months, and so we had time to explore many different solutions. We just saw that the naive approach of just pushing them on the stack was easily broken by separate compilation. We could have some adjustment processes at runtime to deal with the situation, but the costs were prohibitive. So we explore other alternatives like using bigger fixed size slots. But for any reasonable size slot, you will always find a value type which is bigger and doesn't fit. And it was also an issue for some of the platforms we have to support, which tie on stack space. So the size of all the slots were just not acceptable for them. We also explore variable size slots and virtual slots. Could work, but there was a high complexity here, especially for the interpreter and stack working. Variable size slots, if you're trying to do a dump or a swap operation, it becomes very, very complex. But then we realized that the way the values are handled on the stack is just, in fact, an implementation detail. You don't have to specify it. So we just say, let's say the JVM specification considers all values only in one slot on the stack. With this decision, the specification of bytecodes, verification rules, and stack states becomes much easier. Even the generation of code and stack maps is much easier. Even if the spec says one slot on the stack, the JVM implementers are still free to implement the slot design of that choice. They just have to be compliant with the semantic and the behavior. Does it mean that we are giving up with the scalar replacement, the fact of broken down the values into the components? Of course not. In fact, this work will be handled by the JIT compilers. And we'll see later in this presentation, we are doing a lot of work, so the JIT compiler could do that as much as possible. So now we present the changes we've done to the interpreter in the HotSpot VM. So the first step, of course, was to support the new bytecodes and the few overloaded bytecodes without impacting the performance of existing ones. Then we looked at optimizing the interpreter for value types. Unfortunately, the HotSpot interpreter can only see one bytecode at a time, which significantly limits the possible optimization. So we aimed for indirect optimization. If we cannot optimize the interpreter, maybe the interpreter can do something that will help another feature of the JVM. And we decided to implement off-heap allocations for values on stack and local variables. And here the goal is to reduce the workload on GCs by avoiding heap allocation from the interpreter. Doing this, there's still a risk because values can have references in them. If you are not careful and putting values outside of the Java heap, but the GCs still have to manage them, you just have extended the Java heap, so you have to be careful. Focusing on stack and local variables allowed us to have thread local management and recycling, avoiding global operation for that. So just like Gen9, the very first implementation of value types in HotSpot, we were using the single slot on the stack to store an indirection to a value allocated in the Java heap. Because we were in the Java heap, we had to follow the rules of the GC, so we have a header, so the value can be managed by the GC. But this is not a boxed value. This is still value types with all the semantic of the value and not of an object. Then we added thread local buffer. So now the indirection can either be indirection to the Java heap to a thread local buffer. In the thread local buffer, allocations are performed just like in TLabs, so by incrementing a pointer. The management of the thread local buffer is performed with a frame based on a per method frame base, meaning each time a new frame is created on the stack, we remember where the allocation pointer was. A frame can reference values from a parent frame or can allocate new ones. Allocating to the buffer is not mandatory. We can still allocate values on the Java heap. The deallocation is pretty simple. Because we are managing with on a per method frame base, when we are removing a frame, we know where was the limit, where the allocation for this given frame started. So we know all the value besides this threshold are dead values, and we can collect them. The one in the Java heap will be collected by the GC later. Slightly more complex scenario is when you want to return a value. In this case, we have to move the value just after the threshold, so the caller can continue to allocate values just by incrementing the pointer. We didn't want to force each thread to allocate a static thread local buffer, because it's just like extending the stack. We wanted something much more dynamic. What we did is we implemented a global memory pool for all threads. And each thread is building its own thread local buffer by taking pages from this global pool. So the thread local buffer is not a contiguous piece of memory, but a linked list of pages taken from the global pool. We are trying to avoid too many global operations, so we are not returning pages to the pool immediately. We have a local cache of one page, so if a thread is operating at the boundary of 2 pages, we can avoid going to fetch or return page to the global pool too often. If all the pages from the global pool have been used and a thread tries to get a new one, it will get a failure and the value cannot be buffered. So we just fall back to just allocate it in the Java heap. So in HotSpot, you can find values in various formats. They are in the Java heap. You find them with a header followed by the field, just to give the uniformity of all the objects allocated in the Java heap. So GC do not need to be modified to handle them. But they are still Q types, they are not L types. Off-heap allocation performed by the interpreter, we realize that this header is still something very useful. Just, for instance, to keep a class pointer to prevent the GC from unloading the value class we are dealing with. Finally, we keep a header with the same size as the one in the Java heap, which has an advantage, which is the interpreter code and the runtime most of the time can deal with value type without having to consider where they have been allocated, because they have exactly the same offset for the fields. Off-heap allocation performed by the JIT. Values are broken down into pieces, stored in register and stack. This is the JIT problem. Flattened values in arrays of field. You find values without header packed. If we need the type information, we are retrieving it through the metadata of the container. I'm missing something. Okay. So now we speak about JIT support in minimum value type. The first goal was to support all the features, so like new bytecodes, the new data layout coming from the flattening, the buffering, the optimization, a lot of stuff just to get started. Then they focused on optimization, and the first one was passing value types in registers on the stack. And this optimization is possible because we do not have to return identity. The JIT is also trying to avoid heap allocations. It's trying to remove or avoiding boxing from the derived value type to the value capable class. And always important, avoid a regression for code not using value types. So this section has been provided by the Valhalla compiler team. So thank you for their slide and the work they did. So Tobias Hartmann from Oracle, Roland Wessler from Red Hat, and Zoltan Majo from Oracle. Unfortunately, they are not here today. So here an example with a regular Java class describing a complex. And we have a method compute POJOS that just performs operation, a simple operation with this Java class. If you look at the code generated by C2 for the compute POJOS method, you see a very complex code. You can see that here the escape analysis has not been able to detect that the allocations were not necessary. So each branch of this code, you can see some allocation, and you have some load operation to get the feeds from the allocated objects. Now, we are changing the code, very small change, to tell it's a value type. So this is not minimal value type. You are using here experimental JavaC compiler that allows us to directly type and code with value types, which is much more convenient. We have a compute value type method, which is almost similar to the compute POJOS method we have seen before. If we look at the code generated by C2 for the compute value type methods, we can see something much simpler. We have no allocation. We don't even have load operations. Everything in registers. This is what we can achieve with value types. The JITs try to avoid allocation, relying on the property of no identity, all final fields, and no subclassing. They did that by introducing a new representation in the RR of C2 and by implementing completely new optimization, taking advantage of those properties. Inside C2, value types are treated as identityless aggregates, and each field can be passed or optimized individually. So they are not trying to fix escape analysis by using value types. In fact, they are optimizing value types by themselves without using escape analysis at all. There's still a few cases where the JIT needed some allocation. For instance, when calling a method with a value type in argument, or returning a value type, when de-optimizing, and when writing to non-flattened field or array. I will speak about the first two and how they solve these problems. The problem of calling a method and passing an argument is the interpreter is expecting a single slot with a direction to an allocated value types. But the compiled code would prefer to have everything in registers, which is much more efficient for it. By passing everything in register, they are avoiding allocations and store and load operations on call boundaries, which make a huge difference. The solution is when we have a method with value types arguments, what is the method being compiled, in fact, has a slightly different signature internally, which is made of the individual fields of the value types. This way, these fields can be passed in registers. Fortunately, in HotSpot, we already had some adapters for calls because the interpreter and the compiler have slightly different calling conventions. So they modify, they extend the adapters to handle the case of value types. So when a compile method is calling interpreted method, initially all the value has been broken down in registers. The C2 adapter will allocate value types, fill the fields from the field values in registers, and then when the interpreted method starts its execution, it has allocated value type available. When an interpreted method is calling compile code, we are doing the opposite. The I2C adapters take fields from the allocated value types and load them into registers. So the compile method can run with everything already in registers. Of course, when a compile method is calling a compile method or interpreted, or is calling interpreted method, you have no adaptation to make. So we are avoiding allocation or loading. Returning a value type has been a more challenging problem. The reason for that is we didn't have adapters for returning value, for returns, in fact. Some problem, interpreter want to refer an direction to allocate value types. The compile code want to return in registers. Without adapters, we took a radical decision that value types are now always returned in registers, even for the interpreter. It had a huge cost for the interpreter, but it allows the compile code, which is the most important one, to be more efficient. And it's always the work of the interpreter to rebuild value types from field in registers if needed. The problem is how to reconstruct a value type from field in registers. You need to know the exact type of the value type. Can you use it, get it from the signature of the callee? Unfortunately not, because in the MethodHandles linkers, the signature is erased. So the new return convention has one more argument. So when we're returning from compile code, the first thing we find in register is a pointer to the class of the value type being returned. So with this class pointer, the interpreter can rebuild the value type. When we are returning from interpreted code, the first argument is in fact the indirection to the already existing allocated value type. Because if we are returning to interpreter, we can avoid creating a new value type. The challenges of the compiler team has been difficulty to evaluate the implementation because we were starting from scratch. We had no code, no use cases, very limited code, very limited tests. We had to rebuild everything. We cannot reuse anything existing. We had limited benchmarks to see the performance. Now we have some benchmarks and we're getting some very promising results. Method handle chains are being a very hard thing for them. The problem to optimize the method handle chains is due to the fact that lambdas are erasing signature. So the G compiler is lacking type information to perform the optimizations. They did a huge work in situ. They changed the type system, the coding conventions. They really did a really huge work. The limitations so far are that we only support 86 64 bits. Not all C2 optimizations are available. There is no C1 support, which means if you are enabling value types, you won't get tiered compilation. Not all C2 intrinsics are supported. And most of our internal tests are still relying on our experimental Java C, and we are not using minimal value types in most of our tests.
So before I continue, I believe there were some slides missing in here about array flattening. So if you're interested in hearing about J9's work on that, we can maybe talk about that in the workshop later today. So MET, it takes a step closer to value types in the JVM, but there's still more that is needed before we get to full Valhalla value type support. We will look at a couple of the areas that are more, they're not really in MET, but that we are exploring. Instance field flattening applies to both object fields and value fields. So flattening a value field is similar to the way that we do that you have a superclass, because the same way that when you load a class, you need to load the superclass to get the field layout from it because you're supposed to inherit that. The same thing actually happens when you try to flatten a field because you need to load that type as well to figure out how to drop the field layout from your value field into your own field layout. So in terms of field layout, we could optimize for density. We could say, like the problem we saw earlier with the arrays where you suddenly get a lot of padding because you needed to align the longs at the beginning of the value type, but there's a single byte at the end, so lots of padding. You could optimize for that, shift things around and fill in all the padding holes, but that would be a really bad hit on performance. So we don't do that. We take the whole value field layout, the value class field layout, and drop it right into the rest of the field layout for that object. The static fields are not flattened. That gets too expensive when you try to load a class and it immediately starts loading all those fields. With instance fields, you can delay that a bit. So as we talked about before the specifications for MVT and also probably the specifications for full value types, it doesn't require this. It doesn't require flattened fields. It's up to the implementer whether you do it and how you do it. So let's take a quick look at the J9 approach to this. If we start off without any value types, if we have a very simple class hierarchy with a few fields in each class, J9 will do the following. It will start off with the 64-bit values, and so the fields for 64-bit values, and then we'll put the references in the middle because they could be 64, they could be 32, and then follow that with the 32-bit values. So where are the rest of them? Where are the 16 and 8? Actually, J9 doesn't do that. J9, the smallest field you get in object layout is actually a full word. So the way this will look then is that you get your, for an instance of C, you get your header, you get the long J, and then you get your string S, and then at the end you get your single int, and now we're not 8 aligned. Not really a problem, because when B comes after, it doesn't require alignment, so we get a couple of bytes there. Now we're still not aligned, and C actually requires it to be aligned, so we get a little piece of padding in there. The side effect of the way this is done is that you will only ever have one padding, because we keep filling it in as we, if we can. But where do the values fit into this? So what we do is, if we look at a similar example, but with the value, so we have this value 0.3D with 3 longs, x, y, z, and then class A has a field that we'd like to flatten. An instance of B that extends A will start off the same way. We get the 64-bit value, you get your 32-bit int, and then now we have the similar issue as before, except that we suddenly get it in the middle of A, and that is that we're suddenly starting over again with 64-bit values. So now we need to align in the middle of the field layout. So we pad after the 32-bit value, and we start over again with 64-bit. And then when we get to the byte from B, we put it at the end, or we could get smart and put it into the padding. Fred?
So now we speak about a few work in progress. They are just exploration. I will more speaking about the problems than the solutions, that we don't have the solutions yet. Value types in the long term will eventually support methods. There is no doubt about that. They will eventually support interfaces, but we don't know yet which kind of interfaces. Will they be able to support the current interfaces? Do we need a new type of interfaces? This is still an open question, because we have a lot of issues right now with the relationship between interfaces and Java-long object. So many people think that interfaces are subclasses of Java-long object because they have all the methods. In fact, no, an interface cannot extend a class. But in the JVM specification, there is some special method resolution rules that state that public non-static method of Java-long object must always resolve successfully when you are dealing with an interface. Unfortunately, among this method, we can find wait, notify all, which have no meaning for value types who do not have an identity. If you look at signature and all the semantic interfaces are currently considered as L types, which is an issue for Q types, the value types. We also have issues with default methods, because the body of a default method expects the receiver to be an object. And we are also working on value types and generic code. Today, generic code is based on erasure, and so everything is handled as a subclass of a Java-long object. But value types are currently not subclasses of Java-long object. We don't know if they will be or not. Open question. Today, they are not, and we'll get a bit stuck here. So there is a search for new supertype, object or something else. Do we need a supertype for all value types? Do we need a supertype for everything? Object, value types, primitive types would be nice. Is it feasible? We're still working on it. The use of generics and supertype might prevent some JIT optimization. Passing values in registers only works if the caller and the callee agreed on an exact type. If you're using a supertype or generic type, you cannot perform this kind of optimization anymore. The compiler team is already trying to solve this problem with lambdas, because the problem exists in lambdas too. If you want to get involved, there is a mailing list on OpenJDK. There is a repository where you can download the source. Don't forget to switch to the MVT branch, otherwise you won't get the Valhalla bits. In the long tradition of VM exploration, we have a page with a huge list of VM options you can play with. We hope most of them won't survive the project, but so thank you very much. And if you have any questions, we have 45 minutes. Right on time. Thank you very much.